Welcome to This Explainer. I'm absolutely thrilled you're here with us today. We're going to be digging into something that's honestly going on all around you, right at this very second. An invisible, continuous tug of war that dictates how literally everything moves. We're talking about mastering dynamics. You know, it's so easy to look at the world, see a bunch of static objects, and just think nothing's happening. But the truth, even when things look perfectly still, there's this intense, hidden physical battle going on right beneath the surface. Okay, let's dive right in.
So think about this. Why doesn't our resting book just fall right through the table? I know. It sounds like a completely silly question, right? Obviously, gravity is pulling it down, so something has to be stopping it. But how we actually define that something? Well, it exposes a massive, incredibly common misconception about static objects and how forces interact.
Here's our game plan for today. First, we'll look at the Newton's third law trap. Second, we'll get into friction and fluids. Third, reaching terminal velocity. And finally, we'll wrap up with free body problem solving.
All right, part one, the Newton's third law trap.
Okay, take a look at the statement on the left side of your screen. By Newton's third law, weight is equal to normal force. Let me tell you, you will find this written on thousands of failed physics exams. And honestly, it sounds completely logical, doesn't it? Every action has an equal and opposite reaction. But look at the reality check on the right. Third law forces always, and I mean absolutely always, without exception, act on different bodies. Normal force and weight acting on the exact same book literally cannot be a third law pair, by definition. They're really just two separate forces that happen to balance each other out perfectly, meaning the net force is zero.
So then, what exactly is stopping the book from falling? Well, it's what we call the normal contact force. Let's define this really clearly. It's a force that occurs purely due to contact between objects, and it acts perpendicularly, or normal, to the plane of contact. The table pushes up on the book with this force, exactly matching the book's downward weight. But remember, this is Newton's first law at work here, creating an equilibrium where the resultant force is zero. It has absolutely nothing to do with the third law.
Which brings us to a crucial question. What are the true third law pairs in this scenario? Let's untangle them. First off, the table pushes up on the book with a force we'll call R. In response, the book pushes down on the table with an equal force, R prime. Notice how those act on different bodies? Table on book, book on table. But what about the weight? Weight is just the Earth's gravity pulling down on the book. Therefore, the equal and opposite third law pair is the book's gravity pulling up on the Earth. No way, right? It sounds totally mind-bending, but yes, your tiny little textbook is actually exerting a gravitational pull on the entire planet. That is the true hidden tug of war.
Moving right along to part two, friction, drag, and fluids. So once an object actually tries to move, friction steps into the ring. Frictional force always acts in the opposite direction to the relative motion of the objects. It's kind of like the ultimate contrarian, right? Whatever direction you want to go, it wants to pull you the other way. If you apply a pulling force that's stronger than this frictional force, the object accelerates. But, and this is a really vital concept, so pay attention here. If your pulling force exactly equals the frictional force, the object doesn't just stop, it travels at a constant velocity. It's a dynamic tie.
Now, friction isn't just something that happens on hard surfaces. When we transition over to fluids, and remember in physics, fluids mean both liquids and gases, we call this resistance a viscous force, or you might hear it called drag. This force depends entirely on the fluid's viscosity. Think about it. Water has low viscosity, so it's relatively easy to move through, while something like thick glue has high viscosity. Even the air around us exerts a viscous force, which we usually call air resistance. And uniquely, unlike standard sliding friction on a floor, this drag force actually gets stronger and stronger the faster the object moves.
All right, part three, reaching terminal velocity.
A skydiver falling through the sky is just the perfect illustration of this concept. When they first jump out of the plane, they accelerate downward super fast because their weight is way greater than the air resistance. But falling objects don't just accelerate forever. As they fall faster and faster, that air resistance pushing up against them grows stronger too. Eventually, they hit what we call terminal velocity. This is the maximum constant velocity an object reaches when that upward resistive force exactly equals the downward weight of the falling object. The acceleration starts at standard gravity, g, but it gradually decreases all the way to absolutely zero as the drag force ramps up to match the weight. At that point, they're no longer speeding up at all, they're just falling at a steady, uniform pace.
Now, since air is pretty thin, we usually just ignore buoyancy in these problems. But what if we drop an object into a really dense fluid, like, say, thick oil or glycerin? Now we've got 3 specific vectors acting on our object. We still have weight pulling downwards, of course, but pushing upwards we have not 1 but 2 forces, the viscous drag force from moving through the fluid, and an upthrust or buoyancy force because the object is displacing that thick, dense fluid.
So when our object falling through the oil finally stops accelerating, it reaches a brand new equilibrium equation. The resultant downward force drops to exactly 0 when the weight perfectly equals the upthrust plus the viscous force. It's basically a 3-way tug-of-war that ends in a perfectly continuous tie.
And finally, part 4, free body problem solving.
Okay, this 4-step procedure we're about to look at, it acts like a literal cheat code for untangling complex physics problems. Seriously, use this every time. Step 1, you just draw a quick, general sketch of what's happening. Step 2, you mentally detach the object of interest from its surroundings. This is what we call your free body diagram. Step 3, draw and carefully label all the known and unknown force vectors acting on that specific object. And step 4, resolve those vectors into perpendicular components so you can easily apply Newton's second law. Let's actually see this in action.
Here is our challenge. We are looking at a real-world scenario from our source text. Imagine a 5.0 kilogram box being pulled along a floor. The pulling force is 25 newtons, but it's not straightforward. It's being applied at this awkward 20-degree angle to the horizontal. Meanwhile, the frictional force resisting the movement is a flat 20 newtons. Our job? We need to calculate the box's exact acceleration.
So to find the resultant force, we can't just subtract 20 from 25. Why? Because that pulling force is angled. We only care about the horizontal pull that's actively fighting the friction. To find that, we have to resolve that angled force using a little bit of trigonometry. The horizontal component is 25 times the cosine of 20 degrees, which gives us 23.5 newtons acting to the left. The frictional force is acting to the right at 20.0 newtons. Subtract the two, and we find our true resultant force is just 3.5 newtons to the left.
Now for the final step, bring it all home. We take that 3.5 newtons of resultant force and apply Newton's second law, force equals mass times acceleration. So, we divide our 3.5 newtons of force by our 5.0 kilogram mass, and boom, there it is, 0.70 meters per second squared. Just by breaking down the vectors, we completely revealed the hidden math behind the tug-of-war.
As we wrap up this explainer, I want to quickly recap our most crucial foundational rule of dynamics. Read this quote and honestly, lock it into your memory forever. Third law forces always act on different bodies. If you remember this one single fact, you're going to avoid the traps that snare so many people when they try to analyze equilibrium and motion.
Before we go, I want to leave you with a final thought to really test what you've learned today. As you sit watching this right now, feeling your chair pushing up against you, what is the true third law pair for your own weight? Think about what's actually pulling you down and what you must, therefore, be pulling back up. It completely changes how you view your place in the universe, doesn't it? Thank you so much for joining me on this explainer, and remember to keep questioning the world around you.